Welcome back. In this video, we are going to do example 3.6.3. Let f of xy be x squared plus y squared, which is a circular paraboloid. We are asked to verify properties 2 and 3 in proposition 3.6.2 for f at the point A, which is 3, 4. We're asked to graph the situation. Let's remind ourselves what properties 2 and 3 were about. Property number 2, paraphrased, said that the gradient is the direction of steepest descent. And property number 3 said that the gradient is perpendicular to the level curve. So let's start by graphing our circular paraboloid. The circular paraboloid, we remember from our study on quadric surfaces, is a round wine glass type shape facing up in this case. So there we have some axes x, y, and z, and we're asked to investigate at the point 3, 4. So if we draw the image of this point on the function surface, then the level curve that function, or that point is on, is by definition of level curves on the curve with all points at the same height. And the height of that is the function value. So we have 3 squared plus 4 squared. 9 plus 16 is 25. So our point is at a height of z is equal to 25. Now z is f of xy. And so that means that our curve, x squared plus y squared, is 25. And if we embed that in the xy plane, the projection of that curve down to the xy plane will look something like this. Let's draw that curve flat in R2. We'll add the gradient and the direction of the curve, and then we'll embed those things back up into three-dimensional space. So there's our circle. Our circle of radius 5 on x and y axes. And we are looking at the point 3, 4. So let's put that somewhere there. Now, we know we can parameterize this curve. It's a circle with radius 5, and so its parameterization, or one of the parameterizations, is 5 cos t, 5 sine t. We want the direction of the curve, so we want the tangent vector r prime of t, which is minus 5 sine t, 5 cos t. And if we want our radial vector at the point 3, 4, then 5 sine of t is 4, so our tangent vector is minus 5 sine t minus 4. 5 cos t is 3, so minus 4, 3. And if we look at the dot product of r of t dotted with r prime of t, we're going to see, so 3, 4 dotted with minus 4, 3, 12, minus 12, we get 0. The tangent vector is perpendicular to the radial vector. So the direction of the curve is a perpendicular direction. We're going to let u hat be the norm, be the 1 over the norm of r prime of t times r prime of t, the unit tangent vector in this case, and that is going to be calculating the norm of the vector minus 4, 3. We'll get 5. So 1/5 minus 4, 3. And there's our vector u hat on the curve there at a 90-degree angle. Now we are asked to verify that the gradient is perpendicular to that level curve. So the gradient should also be perpendicular to u hat. Well, let's calculate the gradient. Our gradient vector at any point xy is the vector of partials. So 2x and 2y. At the point 3, 4, we're going to have the vector 2 times 3 is 6, 2 times 4 is 8. So if I graph that vector also at the point 3, 4, well, 6, 8 you'll notice is 2 times the radial vector. So it is parallel to that radial vector and twice as long. So there is our gradient vector. And we could do the dot product again with the direction of the curve, but if the u hat is perpendicular to the radial vector and f is parallel to the radial vector, well, that's sort of enough to say that our gradient vector is perpendicular to the level curve. So we have verified property number 3. We want to take a look at number 2. The gradient is the direction of steepest descent. So let's go back to our graph in 3D. If we embed u hat down in the xy plane, it's there. If we take the image of u hat, well, it's going to be along the level curve. So our image of u hat is up there on the function surface. Similarly, if we embed the gradient is going to be perpendicular to u hat. And up on the function surface, the image of the gradient would look like this. Perpendicular again to that level curve. Now, taking a look at the paraboloid, we know that on a level curve, the change in function value there is no change. Right? So the directional derivative, the instantaneous rate of change, is 0 along that curve. And certainly you can imagine it increasing to the steepest point here and then decreasing back to 0. And then similarly decreasing to its steepest negative and increasing back to 0. So visually at least, we have verified number 2, that the gradient is pointing into the direction of the steepest ascent up the function surface. In the next video, we will do a more calculation-based example with example 3.6.4. I'll see you then.